All right, so first, thank you for showing up at the last lecture. Right, so we have 2 more hours in which I want to just cover more stuff to give a broad overview and give you a sense of direction. Where is this thing going, at least in my opinion. So there's a lot of stuff we have not talked about in class, but again, I do want you to make the difference between cool stuff to do for research and useful stuff to do in industry. They tend to be different. Okay, so I will be talking briefly about a bunch of cool stuff. A lot of it, it's even used, not on a big scale. Now, anything that's big is related to web technologies. And a lot of what I'm going to mention is not really tied up into the web technologies, right? I will have some slides on the distributed systems when applied to web, and then I'm going to try to tie all the knots and so on. So I'm going to reserve that for the later part of the class, and I'm going to try to bring everything together in a realistic manner, okay? But let me quickly just go through some of these other ideas and throw something out there to point out what else you could be doing. Now, I will argue in the later part that you don't necessarily want this because it doesn't fit into a bigger kind of plan, but nevertheless. Okay, so one issue I want to first talk about is distributed object-based systems. Right? And to some extent, you're already doing distributed object-based systems. Scala with actors. You could argue it's exactly this. It's distributed object-based systems. It actually has much stronger semantic, which is great, because not only you have this message exchanges. Distributed object systems are really, if you want a generalization of remote procedure calls. So it's not only about calling somebody far away, but there is this notion that the thing far away and possibly the thing close by are objects. So they have encapsulation and all the other good things about objects, right? They are nice, well-defined components. Really object-oriented programming and object-based systems are all about, if you want, this high-level kind of programming in which you have you design components and components come together with other components to form bigger things, right? This was assumed and pushed in a big way for, I would say, more than 30 years now as being the solution for almost all the software engineering problems. Turns out not to necessarily be the case, right? But objects have their own, if you want, nice structure, right? They are nice, confined. They interact in a relatively simple way. So it's all about simplifying the interaction, if you want. Now, I argued throughout the class, and it's almost saddening that that's not happening in this textbook. I argued throughout the class that actor-based systems are better. Actors, if you want, are alive objects. So whatever we mean by object-based systems, they tend not to be alive. They tend to be just some sort of things that are manipulated by some other program. Now, they want to be more general than actor-based systems, right? But keep this in mind as I go through the discussion. They are really just kind of a nice way to pack together structure and a little bit of behavior, but with no association to threads of execution in any way, shape, or form, okay? All right. Now, when it comes to this kind of distributed object-based systems, the idea is you need to do this kind of remote invocation, but at the level of an object. And essentially, what you're trying to do is delegate, right? You're trying to ask a faraway object to do something for you and send you back the result. So it's all some sort of message passing, which is really at the core of, if you want, actor-based systems, right? Now, even before I go further, the actor-based systems bring together both local execution and distributed execution. You've seen how easy it is in Akka, right? I mean, using the Akka framework to get actors that run very efficiently on a multi-core machine and then run efficiently when you put them on different machines and they just exchange messages. Now, of course, you start to pay penalties for latency and bandwidth when you go to a distributed version, a true distributed version of this, right? But nevertheless, the same code with minor variation was good for both local and distributed. Now, these distributed object systems are all about far away, and they don't impose any local structure. And to some extent, that's a pity, right? Why not have a unified thing? But you have to unify that under some sort of a language. I mean, that's kind of the problem. Distributed object systems are trying not to impose any kind of a local behavior. So they don't say you should use objects locally. They just say if you want to talk to somebody remote, you have to use object systems. And they don't impose any kind of language on any other structure. So they are designed to be more general than that. And maybe that's, in fact, a fault, right? And the structure is exactly what you would expect, right? You have the client. You always have some sort of a proxy that does the impedance mismatch in terms of how things can actually be called remotely. The client runs something here, then whatever it needs to do is going to translate in this language that's about objects. And the distributed objects presumably now live on the server. They could have lived here, at least partially. You could have had other choices, but in this particular model, they all live on the server. And all you do is you interact with the objects. Now, any programming language that contains objects will basically use the method invocation as the primitive for the object. I mean, there are special methods like constructors and destructors, but beyond that is really method invocation. Method invocation really can be translated into some sort of a message sent, maybe to a proxy or somebody else, if you're doing this distributed object. So it's really amendable to object-oriented systems. Now, the fact that object-oriented languages in general, right, try to protect the internal structure is actually very good when it comes to remote access, because you're not supposed to know what's inside anyway. So really, there should be at least semantically no difference between calling a method and sending a message that contains the parameters of the method for the method to be executed remotely, because you cannot peek at what's actually inside, right? Now, of course, as I keep on mentioning, this is all dealt with in a much more elegant way by actor-based systems, in which you really do just messages, and there is no method invocation, right? So one way to characterize an actor, if you want, is an object that only processes messages rather than respond to methods. And methods are there really just maybe for convenience and familiarity with the old function calls. There is no fundamental difference between processing messages or versus method calls. Right? I mean, ultimately, it's about making available information in the form of parameters and producing some result, which might be some sort of a return message or things of the sort. Okay. All right, so this is the idea. There is always some sort of a serialization, deserialization, and this is why you need these kind of skeletons, right? Now, you have to remember this, because when the information hits the wire, it's all bits, right? And, well, it's worse than bits, because then you have low-level protocols and whatnot. So eventually, everything, it doesn't matter how cute and high-level it looks, it has to be translated into bits when it hits the network. And that's true also for the disk, and that's actually true for the memory as well. I mean, ultimately, we can only store bits and move around bits. And this is our most basic primitive. Everything else is just some sort of a protocol shell on top of that to make sure that we know what's in those bits. Okay? Now, there are many such object systems, sometimes they are tied to programming languages, right? So for example, Java, it's an object-oriented programming language. Early on, when it started to evolve, the networking facilities were built into it. This is, by the way, one of the reasons Java took off when it took off. Right? The fundamental difference between C++ and Java is that there was a concentrated effort on the side of the Java designers to actually care about networking and to build libraries around networking, and to put both multi-threading and networking very, very much in the core of the language. Right? C++ never had any of these things in the core of the language. Actually, arguably, C++ has almost nothing in the core of the language, because everything got delegated to optional libraries, maybe. Right? I mean, even the basic libraries, they're not really required to be there. Right? Which, for good or for bad, I mean, it's different approaches to language design. Take a languages class, and you might get a different perspective on this. Right? So, for example, the enterprise Java beans is one such object store, and it makes sense in the context of Java. Okay? I would argue that in the context of Scala, actors make a lot more sense. And keep in mind, and this might not be obvious at all, right? Keep in mind that you don't need the same programming language in order to have actors on two machines to actually talk to each other. As long as they understand the wire protocol, what goes on the wire. And one good candidate for that is something like JSON, or maybe a binary version of JSON. There is such a thing. It's called BSON. It was invented by the MongoDB people to make sure that you have a very compact binary representation of JSON. Right? So if you have a binary version of something like JSON or XML or whatever else you want, that's a more generic kind of language, you could have actors in one language talk to something that doesn't even look like actors in another language. As long as they understand what goes on the wire and they understand what the protocol is, send messages and so on and so forth. And the actor model is, in fact, very simple, right? Ultimately. Okay. Now, When it comes to designing these object protocols, you can start thinking about refinements, what kind of models, what kind of types you're going to support. And I don't want to teach in detail any specific such framework because it's unlikely you're going to spend too much time on any of them. I mean, when I come and talk about the web, I'm going to argue that web-based technologies are now much more valuable than any of these things, right? So it used to be the case, for example, that Java was king and everybody was doing Java, and well, everybody who was not doing C or C++ was doing Java, and these things actually mattered. It turns out that they didn't take off as much as we would have liked. The semantic is still very heavy. The web took a life of its own. And now because of all the mobile devices, almost none of this really matters because it's all web technology, right? But nevertheless, I mean, you can look at, for example, 4 types. Stateless. Stateless, what does stateless usually refer to? I mean, I mentioned this throughout the class. Right? Stateless means the server doesn't maintain any state, which means it's pure reaction. You give some information, you do something based on the information, and you send the result, and you don't even remember that anything passed through. Maybe some logging or things like this, right? But you're not maintaining any sort of state on the server that reflects the fact that you process a message. So, for example, pure computation is like this. Please perform this computation for me, you send back the result, that's it, right? A stateful is exactly the opposite, and it's very good, for example, if you have to keep track of something, right? Classic example is maintaining a counter of some sort, just to know how many people, for example, visited the website. That's definitely state, and sometimes you really want to do stateful. For example, file systems tend to be stateful because every time somebody does something to the file system, any write has to be reflected in the state of the file that's actually stored on the server so that any future requests are going to be influenced by this past request. So it's crucial for something like a file system, distributed file system, to have a stateful, right? And then you have other things like entity bins and message-driven bins and whatnot. And at some point, things just become very blurry. What's the difference between this and that and this and that? You can't possibly know this. You have to go to the manual and read them if you decide to use such a technology. But I would say this is 2000-like technology, 2000, 2003 kind of technology. The world has moved away from this. Right? Now, then we have other things like the globe, distributed share objects, so on and so forth. But again, these things used to be cool and used to be deployed in practice. And it's really not the case anymore. Right? Now, the paradigm does matter. The idea that you're going to keep together both the behavior and the state, and you're going to do something far away, it's still a very valuable concept. It's just the particular means by which it's done. It kind of shifted away because of the technology drift, right? So it's important to understand the concept, and this is why I'm even talking about it, right? So sometimes the concept is even more important than the actual implementation. So when you need to design your own, thinking in terms of objects might actually be the valuable thing to do, even if, in fact, the API is going to look more like remote message call or even pure web-based API, as I'm going to argue in a second, okay? And I will try to mention when I talk about web technology what the web-based API is. And to some extent, these things don't require to have any specific API, and they could adapt to things like web-based API, but in fact, they have their own protocol. Right, so globe is like that, and then all kinds of complicated setups with adapters and whatnot. And I want you to understand that the Akka framework, for example, and even the basic Scala framework does all of this stuff for you. Now, the fact that you stay within the same language allowed them to refine this entire process and hide it very nicely from you. The moment you start to switch to different languages, you have to expose part of it, or maybe all of it. Right, all the inner workings. But because you're only doing Scala, right, everything you see here is in fact done by either the Scala framework per se, or one of the libraries in the Scala framework, or the Akka framework that's built actually on top of it, right? So all of these adapters and so on. I mentioned this when we talked about actors way back, right? That in fact you have all of these proxies that are created for you. And when you send a message, somebody else looks on the wire and transforms the wire protocol into something that's an internal actor messaging, right? So any distributed version of an object-based model, distributed object-based model, probably is going to make use of both protocols on the wire and in-memory protocols. And in-memory ones are going to be more efficient, hopefully. Right? You could always use the wire protocol to even talk between actors in memory, but that would be very, very wasteful. Okay, I'm not going to go into these details. They don't matter so much. And all of these frameworks have all kinds of idiosyncrasies, right? You can't possibly code in them without looking at examples or documentation. I mean, they all have their own quirks and their own stuff. And try to stay close maybe to the old technology to be familiar, maybe invent something brand new. I would argue that, in fact, it's better to go with something completely different like the actors. For example, this bind here is not particularly nice, right? So it reminds, in terms of semantic, in terms of name, of just the TPCH kind of protocols, right, in which you're binding to ports and so on. But this definitely has to be a lot more high level and a lot different. So the fact that you call that bind doesn't really help, right? And it seems to be too tedious, right? That's the problem. Right? Pointers and things, and when it comes to parameter passing, it's all done through some sort of messages. And remember, messages are supported as a basic primitive on TCP, right, on the TCP protocol. And the technology stack is very deep, right? I mean, you have all kinds of middleware talking to lower libraries eventually get in the core of the OS to something like a low-level networking protocol like TCP or UDP, and then it goes all the way back. Right? Better not even think about what happens until the information hits the wire, because it's really complicated. It goes through many, many layers. It's amazing that it actually works, to be honest. Okay? It's so complex. Right? So all kinds of things have been proposed both in industry and in academia to deal with this kind of objects and so on and so forth. In the end, the web technologies won. So I want to talk about that a little bit later. So you have this kind of polling interface, non-polling interface. How do you piggyback on top of something like TCP/IP? All kinds of things like that. Right? Now, CORBA is one of the most high-profile object reference systems. And what it does, it facilitates objects on different systems to talk to each other. Again, used to be very widely deployed in the enterprise. In the end, unless you have basically a legacy system, it's now almost fully replaced by this kind of web technologies. Again, for convenience. The trouble with something like CORBA is it's quite complicated to actually implement. It's a very complex specification, right? And you're forced to do things in middleware that sits actually quite low. What I'm going to argue is the kind of technologies that won in the end, at least in the last 7, 8 years, are technologies that are tied up with very high-level processing, for example, that browsers can do, right? So if you can bring these protocols, the implementation of these protocols, very close to the high-level part of the browser, right, then that's much, much better than requiring all kinds of deep libraries and complex things like CORBA and whatnot. Okay. And by the way, there is a similar kind of struggle when it comes to connecting to databases. And none of these things actually are interfaces to databases. So databases have their own world and their own problems with respect to connectivity, right? And that's where you have all those ODBC drivers and whatnot, right? And I mean, of course, an ODBC driver is not particularly good for web interfaces. So then you need somebody else to talk through an ODBC driver with the database and do the impedance mismatch. And it's not good. I mean, for example, why not have a proper web interface on top of a database server? I mean, that's a big question. I mean, why go with ODBC drivers or such things, right? JDBC, it's the Java version of that. And it's not so much that they are bad or good. What it is they are not web-based technologies. They are not web-based protocols. You immediately need another component in front, and they don't really like each other. I'm going to talk about that when I talk about the brave new world of web-driven technologies, right? And what essentially that means is when you design a new version of the systems, you might consider having a native web interface. Right? In that way, you bypass almost anything, okay? Or something else, which I'll describe in a second. Okay, so I'm not going to talk too much about this Globe. Globe is one of the big object systems out there. We talked extensively about synchronization, right? So this, for example, if you need to lock a resource. Now, of course, you should ask the question, why should I bother to lock resources? Do I really need to lock resources? Is this a fancy thing that I don't really need, right? All of these are legitimate questions. We've already seen that none of them can be implemented particularly efficiently, right? But nevertheless, one possibility would be something like this. And all of this object systems will provide some form of synchronizations, which is good in terms of convenience, maybe, but then the semantic potentially gets very complicated. And then you ask yourself the question, again, why bother? Right, so one of them could be, if this is essentially some sort of almost like a ring. We talked about this kind of a technology, right? When some sort of a token, it's actually passed around, and one of them will hijack it and do the operation or whatnot. And this is a central solution for that, right? In which you send the locks, and you get messages whether to lock or unlock. So I had a discussion before class about some kind of a web technology, but here is the big technological question, right, which you will be faced one way or another, or you will participate in larger teams that will be faced with this question, which is you have a lot of solutions out there for almost any such problem, okay? But that doesn't really mean that your life is easier. So you might think that if you have lots of choices, life is good because you can always, I mean, if you have lots of choices, presumably it's, you're going to find a better solution because you're going to find the one solution that fits you best. It turns out that that is not the case, and it's extremely hard to pick a good technological solution for your problem. The trouble is, of course, the fact that you don't really have a very systematic list somewhere that goes through a chart and says, if you need this, you do this, some kind of checkbox, some kind of a process, and at the end of it, poof, comes the technological solution. No such thing, okay? What you have is, especially for the newer technology, especially if it's designed closer to open source, what you have is incomplete documentation, possibly good systems, but with some bugs. Some of the old systems tend to be much better documented, but have documentation in many books that span, right, an enormous amount of real estate on your shelf. It might take you months to understand any of these frameworks. It's very hard to figure out if you're going to push yourself in a corner and not be able to do something. So really the big tragedy with any such technology, and I want you to keep this in mind as we go through the other things, the big tragedy with any such technologies is the following. It looks good for your couple of requirements, okay? And you go on with it and you're convinced that everything is good, but then a new requirement comes along, or it's something you didn't notice before, or whatever reason, right? And then you have to do something a little bit different with the framework. And there is simply no way to do a reasonably elegant solution. And you have to hack and hack and hack. That's what kills projects, okay? So there is no good way to say, am I going to run in a situation like this or not, right? Now, there is something, which is the temptation to build everything from scratch, but that's disastrous as well, because you're going to spend all your time building the thing from scratch. You can always do something that's perfect for you. Putting it together, debugging it, getting it to be stable, it's an enormous enterprise. And you have very good chances to derail your whole process, right? So this is really, I mean, to some extent, an extreme version of engineering, right? This is why, for example, at least I personally, I try to read as much as possible, right? So the breadth of knowledge might matter a lot. Understanding a lot about many things might actually provide you that foresight to pick a technology that will not get you in a corner, okay? And believe it or not, the large companies run themselves in a corner as well. For example, this happens all the time, for example, with any kind of design frameworks, any kind of libraries, any kind of things, right? It's definitely good for something, but am I going to run in trouble if I try to match it with some other libraries, or can I extend it, can I not extend it? These kind of things matter actually a lot, right? Small bugs or small idiosyncrasies, you might be able to just fix if the code is open source with the right kind of license. Maybe, right? Now, a lot of these things tend to be very mature, but being mature is not necessarily a good thing because they tend to be also extremely complex. So they might, in fact, have all the facilities you want, but they are so cumbersome to use, they will slow down significantly the design process. So to some extent, this is a pessimistic view of things, but it's good for people that really kind of get the right vibe and have the right kind of knowledge, because you can just pull out of the hat technological solutions that were under the nose of everybody, but nevertheless nobody found the right combination to make it work, okay? And there is a big, big difference between such combinations, okay? You can literally go from extremely fast development to very slow, very buggy, never keep it together, okay? And I mean, look what the healthcare.gov got us, right? And ultimately, that's a technological stack, and a lot of it, by the way, it's open source, right? So it's not even what you pick, it's how you put it together that matters more. So don't be surprised if you see groups of 4 or 5 people doing miracles that very large teams can't do, right? So but it's really no rule of how big a team you need. And, I mean, the bigger the team, the worse it gets, in fact, right? All right. Now, one big problem is the kind of consistency you usually expect out of a framework. So it's not only about convenience and API and whatnot, but also some sort of consistency. And this is, in general, a very big problem. And it's basically what we've seen throughout the class, right? So the stricter you are about the consistency model, the worse the performance is going to be, and the more cumbersome the inner process is going to be, right? So if you could live with more relaxed consistency, that's always a desirable thing. But then you have to survive on top of that. Right? We talked about this, right? And replication has to be part of it. And that's a big, big question. It's how do you scale and how do you replicate? These are I mean, they kind of go hand in hand to some extent, but these are some of the core issues, right? If my traffic increases by a factor of 10 within the next few days, am I going to be able to survive, right? So you have to design for scalability, right? And again, healthcare.gov, and we've seen how hard it is to design for scalability. They managed to only get something like 20 transactions in the first day. That's not exactly a scalable system, right? Apparently now they are getting something like 100,000 per day transactions. But to put things in perspective, that's still measly. I mean, Amazon does much, much better. Amazon probably it's in the ballpark of 10 million transactions per day. Right? It's not that Amazon spent more money than these guys did to put together the system. So a lot of money does not buy you scalability, and that does not buy you reliability, and does not necessarily buy you a good system. And this is one of the lessons here, maybe. Okay. So replication, we talked about replication and so on. These object systems try to basically just bring it together from the point of view of objects. Again, I'm going to argue later that that's not necessarily something you want to do. Right? Fault-tolerant Java. I mean, you have all kinds of technologies around Java, but I would say that all of them are dying. Okay, that's the truth of it. Right? The world is moving away from Java. You still have a reasonably strong bastion around Java, but almost anything I can think of around Java is not as good as something else. And Scala is one of them. I mean, Scala in many aspects tend to be much better than Java, even though it's built on the same underlying technology, on the Java virtual machine and whatnot. And to a large extent, the reason I like Scala and the reason I ask you to do Scala is the fact that it can benefit of all the Java libraries, but nevertheless, it's a much cleaner language, much higher level concepts, much nicer to design interesting things in, right? So the actor model in Scala, it really makes a difference. But by the way, it's shared with some sort of a Java library underneath, right? So presumably you could write actors in Java, but it's so much nicer to do it in Scala. Okay. Now, security is part of the package. And the one big issue is this kind of secure method invocation. Some of these frameworks have facilities for security. Now, the problem with security is the following, okay? And it's really a big pesky problem, which is almost never you want to rely only on one such thing. You want to bring together, in a large system, you want to bring together many different technologies. The problem is you want to integrate your security architecture, because it's the weakest link that actually kills you. People tend to use the same password in all over the place. It doesn't matter how good the globe security method is. It's irrelevant. If the people use the same password on a much weaker system and you break into the weaker system, you compromise everything. And it's very hard to tell people, you know what? I wanted to use different passwords, different security mechanisms for each of the subcomponents of this large system. It's not something that people are willing to do, right? What people are known to do is pick blue as the password. Apparently, that's the favorite color to be used as a password. I've seen an article, I think, yesterday about this, right? Write the password under the keyboard, things like that, right? So people hate password. People hate security. So a big question is, how do you impose good security in general, but any attempt not to unify the security architecture and to try to have different security in different places, it's doomed to fail in a large enterprise. So that's one of the problems, right? So yes, you can have these things, but if they cannot interface with a more generic security infrastructure, it's not going to be particularly useful. Right? Now, The one thing that can actually be extremely valuable is this public key cryptography. And I do want to give you some idea. I mean, I thought about this, an interesting kind of question. How can you securely distribute files over the internet? And it somewhat fits into this thing. I mean, not quite in line with the secure method invocation, right? But let's go through this scenario. Actually, let's postpone it, but somebody has to remind me when we talk about web technologies. It fits there better. Right? Now, again, why secure? Because any of these things will potentially change the state of the system, and if you have rogue participants into the entire activity that can damage the system, steal information from the system, so on and so forth. Right? The moment you can call methods, that means you can do stuff to objects, and not stuff according to what the manual says. Okay? So trust me, the hackers don't read the manual the way you read it. They read it for gaps. Classic example is injection attacks. For example, SQL injection attacks or other kind of injection attacks on backends. And it's very much possible in here. So what that means is you're trying to fool the system to do something that it was not designed to do. Right? So for example, you can write such an object interface on top of a database, for example. And the idea is, you know what? I want you to send me, let's say, the name and the age, and then some other parameter. I'm going to have some kind of a method on top of one of these objects, and internally this object is going to write some SQL and talk to a database, right? That should be easy. Well, it turns out that not so, because you see this name here? This is a string. So usually a SQL injection attack, I talk about this more in the database class, but a SQL injection attack uses the fact that a query is written in the back and completely hijacks what that query is going to do, right? So an example of a really nasty name, and this is why you have to actually do something called sanitize all of these names, right? In the name, you can do this. You can write something that finishes the SQL query with a semicolon and then writes a completely different SQL query that and then ends, and then you write some bogus thing to let the age and the other stuff to be added. And then the engine will do what you put in the middle instead of what it was actually supposed to do. For example, give me the content of the entire database. A lot of passwords were stolen in this way, right? Now, this is something that happens much more often through web interfaces, but there is a danger that something like this happens through this as well, right? So it's not enough even to make sure that this is an integer and this is whatever else needs to be. This string cannot contain special characters, right? For example, quotes and things like that, right? So injection attacks did more damage than anything else because, see, you can be in and out within a few seconds and still a megabyte-sized database with all the passwords. For example, the kind of query you can write is, select the passwords and the username from whatever, and if the passwords are not encrypted properly, you basically just walk out with all such passwords. You don't even have to break into the system. You don't have to do any of these things. So all of this stuff can actually be very problematic, and this is why you might want to consider things like secure method invocation, cleanups, and whatnot. Right? Okay. So I don't want to say much more about the object systems because, again, they're not really used that much unless it's a back end of some kind of an enterprise. But the world is moving towards web technologies. Okay. There is also this distributed, well, let's briefly do this, distributed coordination-based systems. I mean, arguably, distributed object systems can be used also for coordination-based systems. Coordination is all about getting stuff done together in multiple systems. We already talked about distributed message queues. To some extent, that can be used for coordination as well, right? These things are about either doing something in the same place or at the same time, right? Almost never you want to use only vanilla methods like this. You almost always have requirements that are bigger than that, and almost always end up maybe building your own protocol on top of it. But nevertheless, it's good to actually consider some of these issues, right? One thing that is at least useful is this idea of publish-subscribe system, okay? Now, the idea is great, and some systems actually use this, but it's not as prevalent as you might think it is. So publish-subscribe is related to the following idea, right? I want to tell a system what I'm interested in, or to say, here is something that you might want to distribute, right? So there are basically two actions: subscribe, you tell the system what you're interested in, and publish. And the system, when somebody publishes, is supposed to figure out efficiently which of the subscribers are interested in that particular item, and then distribute the item to the systems. And there are many, many problems, because you could have millions of subscribers and essentially billions of publish. Can you give me a system that's like this? So which is the biggest right now publish-subscribe system? Actually, the two biggest ones.
Probably Twitter.
Twitter is exactly like this. Okay? So what did Twitter do? Did they went there and Google for a good publish-subscribe system and get one? No, they designed their own, okay? Because none of them can possibly do what Twitter is actually doing. Twitter is exactly about this, right? If you subscribe to somebody else's tweets, when they tweet, you get the tweet. But you can ask yourself many hard questions. What does it mean to get a tweet? You see, one is the high-level concept, I get a tweet, and another one is when information moves on the wire. There are many tough questions. And I mentioned this to you at the beginning of the class. Twitter navigated towards a Scala solution, because Scala actors fit perfectly into this tweeting business, right? So a publish-subscribe system based on actors is relatively easy to implement, and it would make a good project for this kind of a class. Maybe I'm going to throw it in and, when I teach it next year, right? Now, there are performance issues related to how do you find matches fast. There is a lot of work in database systems, for example, is how can you find matches internally, and there is a distributed system component, is how can you efficiently distribute this information, for example, reduce the number of messages and whatnot. For example, for Twitter, what you might want to do is bundle together multiple such tweets. For example, if I don't log in into my Twitter account, right, too often, and I'm not really watching the tweets all the time, when I log in, you might give me multiple such messages in a single big message, and that in itself can actually save tremendously effort on the back end, right? So there are many tricks you can do. And to a large extent, the success of Twitter is due to the fact that they could control the process. So it's definitely not easy. Now, there is something else that's kind of floating in the air, at least when the distributed systems community is talking about it. And this is, if you want, at the core of computer science, and I don't want to mention it. We're always looking for very good generic solutions, okay? So what I mean by that is kind of the holy grail of a lot of this computer science areas, parts of computer science, is to find the one thing that can be used for many, many different things, and you just plug stuff in, and it just happens, and it works. Probably in no area things are so far away from this as in distributed systems, right? So Twitter fine-tuned their stuff to be good for tweeting. But you could argue in a very strong way that if you change the requirements a little bit, their solution is even disastrous, if not just not particularly efficient, right? So when it comes to getting the job done, having the ability to fine-tune your protocol to go a little bit at a lower level might actually allow you to do something versus not do it at all. And to a large extent, the object systems are not so popular nowadays precisely because they try to produce one of these generic solutions. They don't even provide building blocks. What they provide is a solution, okay? And that's always dangerous, right? This is one of the reasons, for example, why the world is running away from relational databases, because they are a generic solution for something, and you can find particular solutions that are better. Okay, again, this database class, but different story, okay? Nevertheless, you can ask this question in general, how would I do it? But the particulars matter a lot, and you might find extremely efficient solutions if you constrain what is it that you're actually doing. Right? And Twitter, they are masters at constraining. To some extent, Facebook does the same thing, because basically, when you post on somebody's wall, when you post on your own wall, somehow the information propagates. Again, it's not clear when the information propagates. So it's clear the moment you're looking at it and you do refresh on that page, it makes it all the way through, right? But it's not clear that it was already organized in the back or it's organized as you click. And those are very big decisions, right? For example, even for Twitter. When do I hunt down the tweets? When you look, or beforehand so the look goes faster. If you do it beforehand, you could do a lot of things that nobody looks at. So it's this kind of a interplay between do it in advance and maybe push versus pull kind of. And I should talk about that when I talk about web technology. Okay. Then again, we have all kinds of things coming from Java, Genie, and Java Spaces and whatnot. I know almost nobody using this. I mean, there are some enterprises that use this, right? But again, web technologies use much more. Rendezvous kind of algorithms. Lime. I mean, a garden zoo of these things, right? Context-based routing. These were the darlings of the distributed systems community, right? Almost none of them really are deployed widely. Much simpler solutions, in fact, are. So this content-based routing, the idea is you put information about where a particular message is supposed to go based on the content, and then the forwarding that goes from one machine to another is based on that content and where is it supposed to go, right? So this is a naive solution, and this is a more sophisticated solution and whatnot. But again, this is all great, and it makes for very good papers in the distributed systems community, but it's not necessarily something that will tick in practice. I know very few systems that deploy this at the level of hundreds of thousands to millions of things. And that's where you find out if it works or if it doesn't, right? The moment you hit 1 million users, you're going to make the difference between something that's very cute and something that actually works. And ultimately, much simpler solutions actually work. That's the truth. Right, composite events and whatnot. I mean, again, very, very fancy stuff. The rule of thumb should be, though, the fancier, the worse in the end, right? Fancier gives more convenience for the application designer. But you see, even ask yourself the question, do I really want or care about a solution that I can put together in 2 hours because I have this framework that is very expressive and very easy to use and so on, and I just do my own version of the content distribution engine? There are so many other problems to solve with content distribution, including do I have enough servers, back servers, and so on. Even if you speed up the actual act of producing the content distribution server, you're not speeding up the whole process too much, right? So you might as well take your time to design a better customized solution. And trust me, there are no good general solutions when it comes to distributed systems. They all have problems one way or another, right? The trick, though, is to find the right combination of existing and custom technology to get the stuff done. And it shifts throughout the life, right? So you can bet, for example, that something like Facebook got fundamentally rewritten at least 4 times. The initial Facebook, architecturally behind the scenes, was very different than the Facebook now. I mean, obviously, it's a very, very different kind of scale. And the fact that it looks the same doesn't mean anything when it comes to the back end. I mentioned the Instagram situation, right? When they had clients out there, the moment they reached about 50,000 people using the system, it started to crumble down. And they had to fundamentally rewrite all the back end to survive, right? And they didn't change the application at all. I mean, the application was still the same application. The API was still the same API. This is where the web stuff comes into play because it allows you to truly be generic. But nevertheless, the back end was fundamentally different. They went away from something like a MySQL solution, which completely crumbled, to, I think, something like Mongo, right? But yeah, you have to do it in 3 days. That's the problem. It's the ultimate project, right? If you succeed, you might, each of those guys ended up with many hundreds of millions of dollars. If you don't succeed, you're basically just very tired, and you're still living out of pizza and in a cramped apartment, right? Those guys made their fortune in 3 days by taking the right decision at the right time, and they had the guts not to sleep essentially too much for 3 days to rewrite the whole backend and survive. So they got a working solution in 3 days. So here we go. Right? So no theory in the world can really help you that much in those 3 days. I mean, how much you know, I tried in this class to expose you to many, many different things. How much you know and how much you heard about might allow you to go through this kind of technological shocks when you have to take a different path and switch the technology to something different and to do it in a panic. I mean, this is the biggest problem. In this world, in the technological world, you almost never have time to take decisions. You either go very slow, and then by the time you're done, your stuff is irrelevant, and a lot of companies do that, or you're part of the group that has to move very fast, and then it's basically life in the fast lane all the time, right? And that's when what you know can make the difference between also ran and nobody knows about you versus but you made it big. I mean, you can make it big in many different ways, but okay. So many basically such things like GSpace and whatnot for the content distribution. But again, when you look at who's using it, some enterprises to get some stuff done, maybe. But in the end, web-based solutions are really prevalent and all over the place. And designing such solutions seems to be easier and a more controllable process. So almost anything that you see in today's lecture, in fact, is superseded by web-based technologies. Some of them do borrow some ideas from this, but right? Okay, data spaces. I mean, again, very fancy ideas, right? Data space is almost like databases. So a big question, for example, which has not been touched at all here, is when to use a database and when to use something else. For example, distributed object or object systems, and in general, object systems, right? You still have to think about, okay, what's the substrate? Where do I put them? And it turns out that many communities looked at this. For example, the languages community looked at something called persistent systems, which is another name for some sort of a object-oriented database, right? The database people looked at these technologies, right? And in the end, it's the databases, I would argue, that won. Right? Either relational databases, which are absolutely everywhere, including your phone, or even some sort of a mix between pure relational and object databases like MongoDB. But in the end, it's databases that do all of this stuff. And the other stuff is, okay, very nice, very good ideas, maybe, but it's still not as prevalent as you might think. And databases tend to do things in a more static way, to put emphasis on actually performance. And it's not really objects that live in there. It's more like organized sets of data. So maybe a little bit of a semi-structured data rather than full-fledged object systems. And to some extent, that's due to the fact that it's a little bit easier to understand what the database does when compared to an object system. So in general, you have to resist the temptation to produce overly fancy solutions, right? So sticking with a core that's very clear and relatively simple. So I like the actor model because it's a very simple core. And this is why I encourage you to only stay with asynchronous messages and not try to do any fancy stuff with synchronous messages and whatnot, even in Scala. Because the fancier it gets, the harder it is to understand what it does, right? And understanding what it does is critical in order to do well in the long run with any system. Let me find the web stuff now. So what I'm going to do for the last part of this class is talk about web technologies, and I'll try to bring together kind of everything. And this is really where the world is moving now. Okay? And it's not about presence on the web. It's about everything is based on this web technology, right? You have an application on a phone, and the application needs to pull data from somewhere. It will, in fact, use web-based technology to get that data. Okay? So even if you're not running in a web browser, you're still using web technology. Actually, it's weirder than that. Even when it comes to displaying things and so on, the world moves now towards things that are pulled from browsers. So to some extent, the browser is, or the combination browser and some sort of a server behind the back with some protocols for the browser to talk to the servers behind the back is really what unifies everything. So this is an ad hoc unification. It's really not planned, okay? Well, unless you're Google. So Google, you might not know about this, but it's not even so secret an agenda. How many people know about the Chromebook? So what's the idea in Chromebook? The idea is to make essentially Windows irrelevant. And let me tell you, they almost succeeded. And probably in the next 5 years, they will succeed in a much bigger way, right? So the idea in Chromebook is to get the backend servers to do everything, but to make things look like native applications. And this is why you see web browsers getting extremely close to both native performance and native, if you want, cuteness, right? So I'm not sure if you've seen this new generation of web applications. So what's a web application? For example, the Chrome people have they have a kind of an app store, and they have so-called Chrome apps. What are Chrome apps? Yeah, I mean, this basically is no different than some fancy thing that you might have when you go to your bank. okay? Because it's exactly that. It's just HTML plus JavaScript. Now, it turns out that they put something more in there to make them be independent applications, which is annoying, and they're trying to remove it so you can actually click on one and run it without actually installing it. What does installing it mean? I mean, that always bothered me, right? So right now, you can actually have essentially full-fledged applications running in JavaScript in your browser. And if you put it in full screen, you might not be able to tell at all the difference between that application and a native application. Well, I mean, some of the decoration and so on might look different, right? But they even have versions of them that emulate perfectly the native application. For example, you can now, right, so you have this widget libraries that when executed make the web app look exactly like an iPad application. It behaves like an iPad, everything gestures work and so on, but it's actually a full-fledged web application. Right? Now, Apple doesn't quite like it because then you don't go through their store and you don't pay and whatnot, but it's actually very much possible. Now, because of that, there is interesting kind of pressure on how to design the backend and what to use in the backend, right? You see, if you manage to, in fact, have a web interface, then you can have web browsers from a variety of platforms to go there. You can have phones to go there. You can have servers to go there. A server can talk to a server, so on and so forth. And the protocol itself, it's relatively easy because it's based only on this idea of a URI, right, which is basically slightly enhanced URL. And the URI starts with some sort of a protocol at the beginning and then many, many, many decimal points. It almost looks like a file hierarchy, but in the end, it can be anything from a file access to method invocation, right? So, and by the way, there is no way for you to tell because of all the magic that happens behind the back, all the routing and rewrites and whatnot. There is virtually no system that, in fact, has files now, pure files behind the back. They even have now special libraries to, in fact, have files behind the back. It's kind of embarrassing. Okay, so HTTP / I don't know, CISEUFL-EDU, and then, right, so we talked about this before when we talked about naming. In fact, this is some sort of a go to a server. But what happens beyond this, right, depends very much on the combination web server and other things that are bundled in there, right, and might not correspond at all to any file, right? So it can be, for example, A, 1, 2, and in fact, this is interpreted as call method A with parameters 1 and 2. It's really this idea of, for example, a controller in an MVC framework, the model view controller framework, right? So, for example, Ruby started this to do in a big way, and then, I mean, PHP was adopted, the MVC model, so on and so forth. But if you hook up some sort of a language, some sort of a processing mechanism behind a web server, you can, in fact, do all of this method invocation. So think about it, how convenient this is. You're writing, for example, a phone application. You need to basically ask Google to give you a map of a particular area. Now, how convenient is it to basically just call a certain URI and then just put parameters after it? All you have to do is string processing, right? You're just bundling things in a string, and then you use the most basic protocol, which means, so all you need is some sort of a make the call exactly like a web browser, and whatever you get, give it back to me, and I'll interpret what it is. So what happens more and more and more now is to have these things that don't even deliver something like HTML, that deliver actual content, for example, like JSON. So really what a web app is all about, and I'm going to go through some of these slides, but what a web app is all about is there is some front-end stuff that gets you the JavaScript and gets you the HTML, but most of these things will, in fact, get parameters in and get back something like a JSON. And this is precisely like your remote method invocation, really. Now, depending on how you organize things in the back, that actually correspond to some sort of an object distributed system or whatnot. But this, in fact, is extremely convenient, right? Because all you need to be able to do is form these URLs, namely you need to know where to ask and what's the syntax, and then wait for the result. You get the result, it's something like a JSON. This, if you don't know what JSON is, it's a very generic representation of the data. The JSON itself has some conventions how to represent the data, and then you got your information back. You transform it into internal data structures. So what happens with virtually all the languages, C++, it's always a little bit different because you always have multiple such libraries, but most languages will have a single library. So serialization to and from JSON, it's a basic facility now in a language. For example, Scala has it, right? So in Scala, you can do a to and from JSON. So if you want to send JSON information, which you might want if you send parameters, you take your internal data structure and you say to JSON. If you're getting a JSON and you want to make it a Scala data structure, you do something like a from JSON. And that happens in JavaScript when you're trying to do these things. That can happen in PHP. All of them have some sort of a to JSON from JSON. So really, JSON right now is the lingua franca of the web. Okay. Now, JSON is very different than something like HTML. The problem with HTML is what? That it's all about the looks. Now, what's XML? Dissociate the looks from the content, but XML is too verbose. XML was one of the biggest buzzwords 10 years ago. Everybody was doing XML. I mean, literally, everybody was doing XML. You ask look at the names of products, or look at the advertising for products 10 years ago. All of them had XML in them. All of them have cloud in them now, right? Now it's about cloud, cloud, cloud. 10 years ago, it was about XML, XML, XML. It turns out that JSON won the war, right? JSON is now much more prevalent when compared to XML. And this is because JSON it's more compact, and it's supported in a native way by JavaScript, right? There is no fundamental difference between JSON and XML, by the way. And to some extent, XML can carry with it even information about what's correct structure, incorrect structure, and all that kind of stuff, right? But it just happens that essentially JSON is, in fact, used. Now, the conversion to and from native data structure in a particular language is what makes it very appealing, right? So right now, if you would have to bet on some sort of technology, I would say bet on something like JSON. For example, what we ended up doing when we had to put some sort of an interface on top of C++ written database. It's not quite a database, it's more than that, but right? So we had actors and whatnot running in the database, and we had the Scala front end. Why Scala? Well, I'll talk about that maybe in a second. There is a web framework, it's called Play framework, built on top of Scala, right? It's a full-fledged web server, if you want. So our problem was the database engine had to talk to the web server, and which had to talk to the front end, and information has to move back and forth, right? For example, if you run a query and you get the answer, it's very easy to say, I'm going to use ODBC, but there is no web browser that talks ODBC. It's simply not something that they cared about. So when it comes to talking to databases, then you are in a weird position. The weird position being, you need this kind of the servers or some technology in the server to talk to the database somehow and get the work done. And this is where PHP or Ruby or maybe Scala Play framework comes into play. But it's relatively clunky. A much nicer way to do things would be ask the database engine to just produce directly something like JSON or the binary version, the BSON, right? Which is now supported even in JavaScript. And that might actually be a much nicer and efficient way to get things done, because you can say, hey, you put the result in JSON, and all I need to do as a web server is pass it through to the user. One of the major problems when it comes to scalability, and by the way, this is one of the problems that healthcare.gov actually had, is try to do too much on every click, right? And when it comes to these web-based systems, the fact that you have a web interface doesn't mean you cannot do all kinds of tricks in the back. Right? One of them being pre-compute things. Or, ultimately, this is the decision we took, is get a database to put data already in the format that the client wants to use, as opposed to other things. Right? So we, for example, support directly results in JSON, which, by the way, is very convenient because results in almost any other language, maybe with the exception a little bit of XML, but XML is really too large, too verbose. Tend not to have enough inner complexity to express interesting things. I mean, if you just want to put a table, you can do comma-separated files, some kind of a table. But if you want anything more than that, then that's not appropriate, right? And definitely, internal binary formats that the databases have, they all have their own binary format. And by the way, they are even incompatible from one version to another. Internal binary formats are highly inappropriate. So an interesting decision in the same style was taken by the MongoDB people, which have a binary format inside because you don't want to have necessarily text. But it's a universal generalization of JSON. It's called BSON. The B is the binary. So it's a binary version of the JSON. It has the same structure as the JSON. JSON can be moved back and forth from to and from Bison in a very straightforward way. But for example, integers are represented as bits in there. I mean, strings are strings, but integers are bits, and doubles are doubles, and things like that. And that actually makes for more efficient both transport and processing on top of them. And this is really the internal format of MongoDB. And you can actually have now a to Bison and from Bison in JavaScript in the form of a library to actually do the translation right there. And then you could put on the wire, in fact, Bison instead of JSON. And there is a similar library for Scala and most of the languages. Okay? So, okay. Now I forgot what I was. Okay, so the thing to keep in mind, and I want to go through some of the slides, is this kind of web technologies with some sort of a language behind. HTML and JavaScript are just a way to start right now. Now, here is an interesting thing that it's not obvious at all. And in fact, this is how the world is moving, right? At the level of 2000, we used to have a very static web. So what's static web? That means you're really accessing just files. The files happen to be HTML. You bring the HTML, the browser interprets the HTML and paints stuff on the screen. Okay? It turns out that that is very inefficient because HTML is very verbose. It has to be verbose because it has to contain a lot of information about very repetitive tasks. Now, CSS, the style sheets, help a little bit, okay? Because you can express properties of classes of objects, classes of things that are expressed in XML and so on. But nevertheless, XML is too verbose. I mean, it's verbose by at least a factor of 10, okay? The brave new world of web design, and this is similar to what a native application does, is you're just doing these calls. You either call with simple parameters or you say, send a full JSON. You get the JSON back, and then you're going to take the JSON, which is some sort of a raw result, and transform it into things that are painted on the screen. So what happens is you do a lot of this HTML generation in the browser, in JavaScript, to produce the HTML that then becomes the visible part, right? And this can, in fact, be done to an extreme, okay? For example, you can start from, well, I want an object of this kind, and then you essentially produce, even in the order of 1,000 lines of HTML to paint very complex decoration and whatnot, and resizable, and so on and so forth, right? This is not different than the design of native applications in which you're exchanging data, you're doing some method calls, and from that you go to whatever it takes using the framework, the user interface framework, to paint the user interface. And it's a very nice way to dissociate information exchange in this form from the painting, right? For example, LinkedIn massively reduced the cost of hosting by moving to something called Dust.js. Okay, so let me just throw some technologies at you. For example, when it comes to HTML, to inventing HTML in the browser, most of the time it's inventing anything in the browser, or taking some data and making it nicely looking. One of the key concepts is the idea that you have templates that get instantiated, right? So for example, if you want to design a table, you have to get the actual raw information and put all kinds of tags around it, maybe with all kinds of other gizmos to make the table look good. If you just want a basic table, you can put few tags, but if you want a really fancy table, you need to put a lot of those tags. So this kind of an idea that you're going to have templates in the Java and get information and you mix up data with the template, it's extremely powerful, right? So Dust.js, much cooler technologies are things like Angular. So Angular is really dynamic HTML in the sense that all you do is write these templates, these patterns. It's all content creation all the time in which you mix data, which might live in JavaScript or might come from the wire, to make the HTML come alive. In the end, browsers can only display static HTML. But actually, because they can refresh fast enough at the refresh rate, you can even do animation in HTML, trust me. Right? Those annoying banners that appear on websites that you scroll the window and it keeps on going down and so on, okay? That's all dynamic HTML, in fact, okay? What they do is they intercept the message call, I mean, for example, the scroll. This is why they lag a little bit. They intercept the scroll, and they simply change the property of the window to make it be centered on the screen even if you scrolled, even though the browser says that all the content has to move up. Right? All kinds of pesky things like this. So for all the annoying stuff you see on the web, there is somebody that was very clever that figured out how to do this dynamic HTML to figure out how to trick the browsers in doing it, really. Okay? So Dust.js, Angular. Angular, it's a full-fledged framework. Dust.js is just instantiation of templates. So an example of that could be div, and then maybe double curly brackets and put here age, and then end div. This is a very simple example. So this is a template. I mean, the same idea is in Mustache and other kind of template mechanisms. The idea is I'm going to give you some data that comes in the form of some sort of object. For every element in the object, I might have the property age. And what the engine will do is will replace this special construct, double curly brackets, age, curly brackets, with what was in the age. And in the end, produce actual pure HTML, that's static HTML. On the fly, it's going to do this, in order to fool the browser in displaying information of a certain kind. Now, this can be used to do all kinds of things. Right? So for example, the way LinkedIn is using this is this. If you look at the LinkedIn page, it's very complex. I mean, any kind of modern web page is going to have all kinds of gizmos in it. And some of them can't even be done with pure CSS. Right? Things like you move over certain parts, all kinds of stuff pops up and whatnot. Okay? Great. So if you really want to have that in the web browser, you're going to overwhelm the web browser. For example, ask yourself the question, is it possible to display in the web browser a table that has 100,000 rows in it? Okay? So there is a straightforward way to try to do that, but then you kill the web browser. And there is a very clever way to do that that actually makes the browser very happy. Okay? So the straightforward way to do it is you transform the 100,000 table into actual HTML, and you provide all of that HTML, which has to be parsed and transformed into the internal DOM structure in the browser. And then the browser is basically just extremely sluggish. I mean, it's dying under load. 100,000 nodes, all of those nodes are extremely complex because they have to keep track individual events, mouse events, and whatnot, right? And all for what? Because you can't put 100,000 things on the screen at the same time. A particularly clever solution, and this can be done, for example, with these templates on the fly, is to say, hey, I'm going to, in JavaScript, figure out how much stuff the user can see, right? And then what I'm going to do is I'm going to ask the browser, I'm going to give the browser in the form of DOM elements only the things that can be seen. That's what, 30 things maybe, right? So then what you can do is when the user scrolls, you might think that the scrolling is an activity that the browser does to move all of that painting of complex HTML objects on the screen. But in fact, the scroll, it's intercepted now by your nice Java program that can actually say, you know what? Delete these elements in the DOM and create other elements in the DOM according to whatever templates you have. Now, this is not very different than the technology you usually use in normal UI design, in which you're trying to do the same thing. You're only concerned about the visible part. You're trying to paint only the visible part, so on and so forth, and tricks of that sort. Okay? And with this, by the way, you can view even a 1,000,000 entry table and have absolutely no problems whatsoever. Right? You just scroll, no problem. Because, you see, having a data structure that has 1,000,000 things in it is not that big of a deal for modern JavaScript. Painting 30 elements on the screen is not a big deal at all for a web browser. But having a DOM of size 100,000, that will kill the web browser because of all the complications that come with the DOM. DOM elements are extremely complex, right? That's what I want you to keep in mind. OK, so you can do all kinds of things, but again, the main idea is you have this kind of a possibility. You ask for data, you get data, and then everything else happens in JavaScript. So you don't necessarily have to move the full content that consists in what is it that you paint on the screen. For example, LinkedIn, because of Dust, massively saved on backend infrastructure. Why? Because when you log in into your page, they say, OK, Aline logged in. Then what they say, OK, no problem. Here is 1 megabyte compressed, so it's going to compress to 100 kilobyte object that describes everything we know about Aline. And trust me, it fits in that amount of data, right? So then in a single message, in a single request, you got an object that you push in JavaScript that contains everything. if you're not trying to very fast paint changes to the screen, right? In a very compact way, you can represent everything that I would ever want to look on that page with a single call. So in 1 second and a little bit of traffic to the back, I got my message, and then I can spend even half an hour and not exchange a single message with the backend. So it's clear what happens here. So all the information about who I am, whatever, who are people that I might or might not want to look at and whatnot happens, all of that can be captured in these complex JavaScript objects, right? The same kind of thing happens, for example, when you do the auto-completion, right? So when you go in Google now, you start typing, right? And Google starts to show you stuff. What exactly happens there? Well, here's what happens. As you type, a message goes on the wire and tell Google another letter of what you typed. Google is trying to run a query. If it comes late, it's no problem because it's simply not going to display it. And it will send in an asynchronous way messages back to the front end, which are in the form of these JSON objects, to say, here is a list of words in a certain order that you could use to autocomplete. It's trying to actually do things ahead, because if you only do one letter at a time, it's too slow. So it might basically send a much larger object, which does come in that 1 second. It increases the traffic, but that's not necessarily a big problem, right? So that in JavaScript, you in fact have many possible continuations, and when you press another letter, it simply finds the best one, and possibly even runs an algorithm that sorts them in the right order in JavaScript. So really the combination now of lots of activity in the front end and only serving data in the back end is what's prevalent now on the web, and not that static kind of content. The problem with static content is you have to do a full refresh of the page. And those are extremely annoying, right? I still don't understand why big websites are not detecting my browser and doing much better. Right? Page refreshes are annoying because there is a flicker in the screen. You click on something and there is 1 second in which you're just staring at the screen. Especially if you have to go through many, many pages, that's really annoying, right? I'm sure you like much better websites in which, even if you click on something, only maybe a part of the website gets refreshed, but most of it stays static. All of that means this kind of ask for something, get back, content, pure content in the form of JSON, and expand everything else in JavaScript. It's really even a form of compression if you want. And it's a very clever one, right? But the net result of that is the fact that this kind of a paradigm in which you either send parameters in this way and you get something back, or it's the difference between get and post methods. You can actually send a document, and this is how you do uploads of files. You can send a document which in fact is a JSON, and get back some kind of a reply. For example, you could even talk directly to a database server in which you say, hey, here is another version of whatever large object. And the database puts in the database and sends some sort of an OK, which itself is a JSON object. Hey, great. That's a nice way to get things done. So this pathway is really well perfected in all the modern browsers and in all the modern backends, right? And it's what I would strongly recommend as the basic technology for almost anything you build, and not necessarily any other kind of protocols. JSON in, JSON out, or simple parameters in, JSON out, right? Yes? RESTful? Well, so all of that idea around RESTful and whatnot is really tied to database operations, right? And to some extent, you don't even have to do a full RESTful thing. You see, here's the thing. Once you have this mechanism, things like RESTful, which is basically just some sort of a convention with respect to what kind of activity you're going to have in the back, it's so shallow that you can do your own version and not suffer too much. So it's not clear at all that you, in fact, have to adhere to an actual RESTful interface, right? So, for example, we use the Play framework, which is a Scala-based framework. And what we do is, once the JSON comes in, I mean, even if you don't have JSON coming in here and you have actual arguments, right, you might actually transform it to data structures that are equivalent to JSON. Or if you get JSON, you transform it into some kind of a Scala data structure. You can even use actors internally to route things and do very complicated stuff, right? So the brave new world, and this is similar to object-based systems, is to, in fact, keep the objects in something like the framework, in the Scala framework, right? The objects are in the form of actors, and that makes it very, very convenient. For example, if you need to perform an action on a database and it takes a while to perform the action, then actors are really a godsend, because all you have to do is say, I already have an actor that talks to the database, and that guy is responsible, and when the database comes back, maybe in 30 seconds, or maybe it sends all kinds of intermediate things in the meantime, you route them, and then you say, OK, I'm done, right? So this asynchronous, so this idea of messaging, messages going back and forth, and data moving around, and not actual content, HTML content, right? It's really what allows you to do extremely sophisticated applications like this in a relatively straightforward way. There is a big benefit of this. If you want to now go away from a web browser and to do just an iPhone application, exactly the same API is what you need. And this is what these applications do, right? So you have a web interface and a phone, iPhone or Android interface, that in fact behind the scenes are exactly the same. And the server couldn't care less which is which. If you only transport HTML, obviously HTML is not particularly useful on an iPhone because you need to use a completely different AI. But if you isolate it, if you separate it, the data from how it gets painted, one of your biggest problems, it's already solved. How do you do a design for a good backend, right? So kind of one thing leads to another, and you're going to have a very nice architectural stack in which you have some sort of a server behind that will understand JSON. We even have servers now like Node.js that are implemented in JavaScript, and they talk JSON in a native way. So it's not even clear you need something like Apache, because Apache was really designed to serve files, not to serve dynamic content. It was adapted to talk to somebody else who can deal with dynamic content. And I have a slide about that. But even with respect to that, things are actually moving away. So things are moving away even from servers like Apache, because it's not clear at all that you want, in fact, to serve files in any way, shape, or form. Beyond, give me the code for application. So beyond the normal frame, HTML frame for your entire application, and all that JavaScript code, which could be much larger than the HTML code. And that's the case in our application, for example. You might never, ever want to get any kind of how do things look from the backend server. Even if you get files, those are data files. Okay? Right, so this is kind of the typical scenario. Right? You have the browser. Of course, it does networking, or whatever form it does, and the information gets to the web server. The web server might talk to some sort of storage. You can do in-memory storage. You can do, you have both in-memory databases now. You can, on this database, you could have a large database cluster, whatever is it that you're doing there, right? But if you have something like Apache, it might actually be in the way. And this is, for example, why the Play framework bypassed completely Apache. I mean, ultimately, what does a web server do? Listens for connections. When a connection comes, interprets correctly the request and serves things. It's not even files, because Apache will basically, the moment it gets to the slash, right, it knows from the routing table that it has to give the control to something like PHP, and PHP will take over this, the rest of the parsing, will do some activity and produce some sort of a result in the form of whatever the user expects. I mean, ultimately, it's all text or it's all bits. You can send whatever you want back. If it happens to be HTML, it happens to be HTML. Now, obviously, you have to know you're getting a JSON here, right? So there is a protocol there, maybe explicitly, maybe implicitly, right, that says if you make this request, you get the JSON back. But if you design such a web application, most of your things will just get some sort of a JSON back, right? And a very nice shortcut, and I want you to understand the power of this, a very nice shortcut is to pre-compute answers on the server directly in JSON, right? So I was faced with a decision like this, right? So you see, the big question is, if you pre-compute stuff, you pre-compute them as what? For example, imagine that you need statistics coming from a large database. And for example, eBay has this problem. So a big problem eBay has is when you're looking at particular items and whatnot, they have to show you the current bid price and time and whatever other information. Now, it would be nice to say when you, for all those hundreds of items on the page. So you see, when you go to one of them, you could justify some sort of a database query to hunt down that one object and get the information about that one object. Because you expect people to spend at least 10 seconds or more on the page, and usually people spend minutes on the page to look at details and whatnot, and then you've done one database request, and you can't have more than one such large request per user, per maybe on average about a minute. Okay? So that's not so bad. But if you have pages and pages and pages of items, and you have to make either an overall query, right, that goes and gathers the statistics and so on, you can actually overwhelm the database backend. So eBay early on, and by the way, this is why eBay is eBay, because they figured out these tricks. eBay early on said, hey, we're not going to go and run all of these queries every time somebody looks at the list of items. We're going to pre-compute them every 1 minute, let's say. You run a single big query every 1 minute, and everybody just pulls off from some kind of an in-memory cache of that 1 minute. So this is why you see things a little bit off. So you might see one price on one item, especially the hot items that move very fast, right? You might see one price on one item, but when you go and look at what's inside the item, it's actually, the price could be vastly different. But again, that's the kind of compromises you have to make in order to keep the system running. You basically are betting on the fact that users are not going to be particularly upset if such a discrepancy happens. Humans are very good at coming up with explanations, and everybody has their own explanation why that happens. But anyway, I don't know anybody complaining too much about that. They know that if you really want to find the price, you have to go on the page. But you get some idea where it might be on the main one. But that's essentially a caching trick. Rather than run many, many small queries, you run a single big one every 1 minute or every couple of minutes, right? But if you do so, the question is, in what format do you put the result, even on the disk? You might actually be much better off, especially if you produce a result that's for one user, to already put it in JSON format. Why? Because all you need to do then is serve a JSON file, and you're done. You see, the trick to survive with many, many users is to try to make the web browser do the work and not the backend do the work, right? So the web browser is really not some skinny little thing that cannot really do much. It's a monster that can do all kinds of things right now. By transporting only data and pre-preparing some of the data, you make the browser sweat. This is what LinkedIn did with Dust and other technologies. I send very compact JSON. You blow it up into very fancy HTML on the fly, and then I can even actually deal with things that are 100,000 entry table, right? Definitely much more scalable because the browser just transports a simpler thing. And the most important thing is I'm not doing database queries to run it. It's the database queries that kill you because database engines are not as fast as you might think they are. Okay? One of the problems, for example, in healthcare.gov is precisely the fact that they have this extremely complex query. So knowing SQL, I mean, I have to warn you this, right? You're taking database quizzes and so on. Knowing the more you know SQL, the bigger the danger you're going to write these nasty queries that are going to kill performance, right? So if you, in fact, have to run a complex database query every time somebody clicks, and that's literally what happens, then yes, it was very fast prototyping because you put all the pressure on the SQL query. But the moment you reach a couple of hundred users, the whole thing crumbles. Because database, especially when it comes to aggregate queries, right? For example, you say, find me all the items that have the price larger than the average price. It's the kind of stuff that you see in database classes. Now, that's one kind of query that kills database. They don't like these aggregate queries, right? Because they are really trying to provide very strong guarantees that the average is up to date and everything else, right? So you run one of these, you paralyze the whole database. Okay? So all the ideas that we've seen in this class, caching and so on, come together, but you have to take it one step further, for example, and pre-prepare the answer in the format that the front end expects it, right? Now, we have all kinds of web documents and whatnot. I don't want to go through all the details. You're all familiar with this kind of things, right? And the nice thing is the browser now knows how to deal with them, including PDFs, right? Most of the browsers have native PDF views, which is convenient because I don't like that Adobe Reader, to be honest, right? If I click on something, I want the browser to take care of it. And this is the idea behind Chrome. So do everything in the browser, right? And what I mean by everything, everything. They even have now support for file systems. It's not prevalent in all the web servers, but you can even have a local file system, and you can even do file manipulation and so on. There's a new API proposed, and I think Chrome supports it. Chrome is really at the forefront because it's crucial for web applications like Gmail. I mean, Gmail, put a web browser in full screen, and Gmail, there is no fundamental difference between Gmail and a native email client, right? It doesn't even behave like a web page at all. Unless you remember something is wacky and you press Control-R, which we don't quite like, right? But other than that, because then they show you that loading, right? To remind you, there is no reason to really press Control-R because you can refresh and you can do things from the application itself. And what happens there? Well, for example, if you want updates to your emails, you can open something like a WebSocket and you say, hey, every time, it's a publish subscribe system really. Every time there is an update, send it on the wire. And then you just write JavaScript code that says, okay, if a message comes on the wire, look at it. Is it an email message? Good. Put it in whatever data structure I have that displays the email, refresh the screen, and so on. So a lot of this kind of stuff going on. Now, AngularJS is something that Google people invented and came up with, but I don't really think it's used by their web apps. They have other gizmos, and maybe they should switch to Angular. So I'm not going to go through this. I mean, you're all familiar with it. And it's really very complex architecture. It used to be like this, but now it's even, if you want, nastier, in which you have some request. This is the web server. The web server, depending on when it parses the request, has some routes and might fire up a so-called CGI program. CGI is these dynamic content programs. Now, the basic technology is really CGI. So there is some sort of a protocol at the lowest level, but is now completely superseded. And internally, it's still a CGI, but it's superseded by things like PHP and whatnot, right? And then these guys talk to the database. The web browser doesn't know how to talk to the web base. And the ODBC interface is here, which is actually very annoying. If you would have a native interface, a native web interface on top of the web server, you could actually directly talk to the web server. There's no reason not to, in fact. And I mean, systems like MongoDB, in fact, have a direct web interface to the backend server, right? But the idea in CGI is you're going to do actual processing. Now, this is still old school, because usually what happened is you pull information from the database and you do content creation in the CGI program. Here's where you render complex HTML, and then you push it in the front end. But if you do so, you're actually overwhelming your HTTP server, and you're overwhelming your backend server, right? So this is why you need thousands of machines if you're using this technology, because you have to cook up the HTML that goes in front. So you're going to have all that traffic and all that computation to put a pretty face on top of the database. A much more scalable solution right now, and this is basically what I suggested in the last half an hour, is to ask the database to directly produce JSON. You just serve the JSON, which is far more compact, and do all of this stuff in the web browser with JavaScript. And JavaScript, it's basically fired, I mean, it's on in all modern browsers because we figured out how to make it secure and so on and so forth, right? That's a much better way to distribute the load. Now, make no mistake, somebody has to do the work. But the trick is to make the client do the work, not the server. I mean, I'm sorry, there is another big benefit if you do so. And maybe this is the kind of stuff I want you to remember. The more you do on the client, the better the user experience. Because there's no need to go back to the server. You see, the problem with the server is not so much that you have limited bandwidth, but you always have limited latency, right? So limited latency essentially puts a strict limit on how fast you can get things back. Unless you can do prefetching or, I mean, push requests in advance and so on, there is no way to mask delays in go to the server, do something, and come back, right? Which means you're going to pay realistically at least in the order of 100 milliseconds. 100 milliseconds is already bad because things flicker, things get delayed, right? What's the hallmark of a good interface? When you click on something, it happens, right? Not click on something and there's a little bit of delay. I mean, it's so annoying to have that little bit of delay. If it's a 1 second, it's really, really maddening. And they've done studies. If a page loads slower than something like a second, people abandon it with very high probability, right? So for example, Amazon can't afford to have big delays, definitely delays bigger than a second, because simply people go and buy on another website. It's so annoying, people just leave. So if you want to do a very interactive, for example, application in the web, right? It's critical that you get big things and you push them all the way in the front end. And you do all the magic in the front end, both the computation and so on, because you have good chances to get it at that 30 millisecond level, right? Humans don't work below 30 milliseconds. I mean, some gamers claim that they can perceive things below 30 milliseconds. 30 milliseconds corresponds to 30 frames per second. Now, the visual system might be mildly happier at 60 frames per second, but it's highly debatable. When it comes to user interaction, even 50 milliseconds is more than good enough. You click on something, a 50 millisecond delay between you click a button and the button doing something, you're not going to perceive it, right? Even 100 milliseconds, you start to perceive. 200 becomes mildly annoying. 1 second is extremely annoying, right? So this kind of stuff might matter, for example, if you're trying to display these graphs based on user interaction, and you have to go back to the backend server. Not only you do work in the backend server, but you have these latencies and delays and flickers in the web interface. So to a large extent, everything does come together. And there is very little limit in how big these JSONs can be. You can easily transport megabyte or sometimes even gigabyte JSONs. I mean, gigabyte is kind of too much because it takes too much time. But what's not out of the question, I want you to understand that this is more than acceptable, is to, in fact, transport all the data. Okay. So a classic example of this, I would say, is things like, I mean, on healthcare.gov, they have this data set that gives you an idea in every state, for every county, for every different kind of plan and some other decimal points. What are the prices for various categories? Okay. Now, me as a person, I might want to investigate, for example, do a thorough investigation of that data. And for example, in the interface they provided, I mean, they have a little bit of an interface in which you click through some kind of a wizard, but that's very annoying. If I want to do some analysis on that, I mean, suppose I'm an analyst, even if I want to look at the table, if you're only transporting the things I can see on the screen, then you have a very poor interface, because every time I scroll in the table, and by the way, this is the interface they have, because they use a system called Socrata, right? Paint some kind of a thing and tells you the table has almost 45,000 rows in it. You say, OK, good, I want to see it. You scroll down, they make another AJAX request, they get another piece of JSON, they get it, and they paint it on the screen. But this is really annoying, right? Because there is almost a second delay between me scrolling down and you getting back the answer to be able to paint the screen. So you scroll, it takes a second to paint. Scroll, it takes a second to paint, right? It's as if you would play a video game that runs at 1 frame per second. I mean, it doesn't get worse than that, OK? And you might ask yourself the question, OK, fine, but what could you do? Well, it turns out that in less than a second, you could transport all of that data and keep it in the browser. So when you go on that page, you could transport the 45,000 rows, and then you could, in fact, manipulate them and provide an amazing experience on 45,000 rows in which you could scroll through tables at amazing speeds. I mean, you can get the scroll bar and go at any speed you want. I mean, we've done this, right? You can do whatever you want with the scroll bar, and the web browser keeps up. Why? Because it's only painting the visible part. And in JSON, 45,000 rows is nothing, right? You can actually do all kinds of complicated things on this. I mean, I will show you a demo, but we managed to damage it, right? Did I show you the healthcare demo at the beginning of the class, the Medicare demo? Right, that table, it had 163,000 rows in it. So it takes 2 seconds to get the data, but once you got the data, you're done, right? So I pay for some bandwidth. I don't pay for latency and do no database request. I just serve the file. By the way, the data, when compressed, is not much bigger than a decent-sized image. Right? So this is my rule of thumb. If all the data is roughly the size of the data that you use for the banners you put on the website, then you definitely should transport all of it, right? So it's almost nonsensical. They push the banners through to make sure that you see pretty pictures around, and that's much larger than all the data that you could actually send in the form of JSON, or you can do even more compact representation, especially when compressed, right? But still, nevertheless, they do all of those independent requests, and those kill the server, because the server now, it's given a JSON object that says, you know what? I want you now to give me row 345 to 386. Has to figure out where it is, what it is, do all kinds of complex processing to get a little bit of something and send it back, versus just give me everything and I'll deal with it. Right? So for example, in the application we are designing, we literally, when we start the system, we say, OK, give me the entire schema of the database, because I want to allow the user to browse through what tables are available there. Give me the full structure of all the files that the user has. Not the files themselves, just the directory structure. Why? Because you see, even if the user has 100,000 files, it's not a big deal to put it in the front end, right? So a couple of these big requests when the application starts, and people know when things start, they're a little bit slow, and you're done, you're set, right? You never, ever have to ask for what the schema is, and the engine will basically notify you when the schema changes and send you another copy of everything. So don't neglect these things that sound counterintuitive, because you might actually have the feeling that you're better off by saying only deltas, not necessarily. The latency, it's really what kills you. Bandwidth, it increases over and over and over, right? I mean, it's not so expensive now, even when you have a server, to have quite a lot of content delivered in terms of throughput. But killing the database is the #1 problem right now. Having overly complex things happening in here. So simplifying the server is the key to scalability. So when you go and design things out there, I mean, you're eventually going to graduate and go do stuff and so on. Think more from the point of view of how could I push stuff from the server to the front end, because the front end, even the phone, it's amazingly powerful, right? Let me tell you how I know. that kind of Medicare stuff, right, with 163,000 rows and whatnot, right? I ran it on my phone. And I mean, look, it wasn't super fast, but it was workable. Now, if my phone could deal with a table of size 153,000, you should have no mercy on pushing things in the front end, right? This does simplify in a massive way the design of the back end. You can think more to use the database to pre-compute things. You put them into JSON files, and then you serve them as files when actually needed, if you can. Or run something like Play Framework, cook up things in memory, in Scala, and just send them as JSON. Right? By the way, it's rumored, or well announced, maybe, that this is how they are trying to fix the problems with the scalability problems with healthcare.gov. They made the mistake to publish the code, and people start figuring out, oh, you know what? These are all the mistakes that you've done, right? It's all textbook mistakes. OK, so you put too much pressure on the database backend. All of this stuff could be pre-computed, just serve JSONs and so on, right? They should have done that from the beginning, right? This is why you need to know about stuff. This is why I'm telling you about stuff. Anyway, it looks like our time is up. So I hope you enjoyed the class. We have one more quiz, and you have to show me something cool in a week and a couple of days. Right? And show me something cool, either in terms of how nice the results are, how good it looks, how useful it is. Right? It's your chance to really do something that can be shown to potential employers, to bring together all your skills. And I want you to capitalize on your skills. This is why I don't want to impose a particular problem on you. OK? So thank you for showing up. And I hope to see you in some other classes, maybe the database class, which is its own set of fun.